Okay, so a little bit of vocabulary we got to start with first. A polynomial is an expression of more than two algebraic terms. Should that say more than two? I think it should say more than one. I think I've messed that up. Poly means more than one. Maybe I meant to say two or more of more than one algebraic term. Let's change that to one right there. It's my fault. More than one algebraic term. And terms are separated by plus or minus signs. So, for example, if I had 3x squared minus 4x plus 2, then that would be 1, 2, 3 terms. Okay, so you got the terms separated by those plus or minus signs. Okay. One thing that we'll talk about with polynomials is the degree of the polynomial, and it is going to be the greatest exponent of a variable in an algebraic expression. So it's the highest exponent that you see. So these are just phrases that we need to know so that we can talk about these correctly, because often you'll see problems that refer to the third degree binomial. And if you don't know what those words mean, then you might get really confused by that, but it's just naming what that is there. So there are special names for polynomials, both by degree and by the number of terms. Okay? So by degree, if you have x to the 0 power, the tricky thing about that is it's not going to be written as x to the 0 power. It's just not going to have an x at all. So it would be like a single number. Then that's called constant. If you have to the first power, it's linear. Second power is quadratic. Third power is cubic. Fourth power is quartic. Anything 5 or higher, you would just call it a polynomial of blank degree. So if its highest exponent is 5, you would say a polynomial of 5th degree. If it's 7, you'd say a polynomial of 7th degree. So there's no special names once you get to 5 there. By the number of terms, technically, put a little star right here, technically this is not a polynomial, but I didn't want to make a separate thing for it. If you only have one term, it is a monomial, and monomials are not polynomials, because what does that prefix mono mean? Just one. Poly means more than one. So technically, a monomial is not a polynomial because it's just one single term there. Binomial is the phrase we're going to use for something with 2 terms. Trinomial, 3 terms. Anything with 4 or more terms, you just say a polynomial with blank terms. So 4 terms, 7 terms, 20 terms, whatever you're talking about there for those. If we were wanting to name these polynomials by the degree and the number of terms, okay, then typically you put degree, the word for degree, first, and then the number of terms second, because this special name for the number of terms is a noun. It's a monomial, binomial, trinomial. and these are adjectives right here. So we typically put those first. So if we are looking for the highest degree here, you are just looking through at all of your exponents and you're finding the highest one. It does not matter what order they're in. We don't add them together. We just look for the highest exponent. So whenever I'm looking for that highest exponent, right there it is for this problem. A degree of 3, if you look at that chart, has a special name. It is cubic. Okay? Then you need to think about the number of terms. So terms are separated out by plus or minus signs. So 3x cubed is a term, negative 4x is a term, and 7 is a term. We have 3 terms, so we would call this a trinomial. Does that make sense? Try naming the rest of these for me on your own. Use that chart and try naming the rest of these. Let's see, Carson, what did you get for example 2? Quadratic binomial. Beautiful. Quadratic, because your highest exponent right there is 2, and binomial, because you've got 2 terms. Okay? Hunter, what do you have for example 3? Say that again. It's polynomial with degree what? Not quadratic. And not trinomial. You are on the right track with polynomial with so many of a certain degree. What's your highest exponent that you've got here? 5. Right, so we're just looking at that highest exponent. And on our chart, there's no special name for that, right? So it's a polynomial of 5th degree. And how many terms do you have? We got 4. And if you look on that chart, there's also no special name for that either, right? So we could just say with 4 terms. So that one's like an exception on both counts, right? There's no special names for it either way. Cannon, what have you got for example 4? Very good. Quartic monomial. There's only 1 term, and your highest degree is 4. Okay? All right, Joey, how about the last one? Okay, binomial, I agree. What degree is it? It is not constant. This one's a little bit tricky because I need to think about the highest exponent, but I don't have any exponents, right? But, Joey, with that x right there, what exponent would that x have if it had one? If we wrote an exponent for it. What? It's going to be what? Okay. Whenever there is no exponent, it has an exponent of 1. And what is the special name that we use for 1? Linear. So that one was a little bit tricky on that. So if you have an x, then that x has an exponent of 1 even if it's not written. Okay? This stuff we need to know just because they like to throw it in places like whenever they're talking about these. Okay? All right, a little bit more vocabulary. So for everything that you've seen so far, zeros are the x-intercepts of a function. These also sometimes are called roots. We are also, so whenever we're talking about these, the fundamental theorem of algebra deals primarily with zeros or x-intercepts of that function. These are sometimes called roots. They may use any of those three words right there to talk about the x-intercepts of the function. In addition, another thing that you might see is solutions, which technically aren't really from the graph, they're from the equation, but can be found from the graph. And solutions are the values that make an equation true. So if that equation is equal to 0, it is also an x-intercept or a root. So all of these are words that we're going to see. They're going to use them interchangeably. Right? It might say find the zeros of the function, or it might say find the x-intercepts of the function, or it might say what are the roots of the function. So those are all things that might be used. So the fundamental theorem of algebra. So everybody get your head up, make sure that your neighbor is paying attention. Tell them they don't want to miss this, because it is the fundamental theorem of algebra. All right. So the fundamental theorem of algebra states that every polynomial function of positive degree n has exactly n complex zeros. And I also could change that to roots as well. We also could use the word roots. Now, we don't really want to use the word x-intercept here, because what we're going to see today is that zeros sometimes don't show up on the graph. Sometimes they are not x-intercepts, but they would still make the equation 0. A new definition for zeros is zeros are values that cause the function to have an output of 0. Now, in most cases, that is going to be an x-intercept of the graph. Most everything you've seen so far, it's the x-intercept of the graph. It's where it crosses the x-axis. Because if you plug in 2 and you get out 0, right, that point is going to be on the x-axis, right? But there's something else that we'll have to consider as we go throughout this chapter, this unit. So, there are two types of zeros that we can have. And the second one might make you angry. But we have to learn about them. So, there are real zeros, and these are just the x-intercepts of the function. This is what you've seen a lot already. So whenever you were looking at graphs that we've already looked at this year or before, a lot of times they'd ask you for the x-intercept of that graph, right? So we've seen those. You can see them on the graph. It's just where we cross the x-axis. However, we also have imaginary zeros. That always makes this word imaginary, always makes kids a little upset about math in general, that why we would care about something that is imaginary. These are values that cause the function to equal 0 but do not show up on the graph. These values include the imaginary value I. Imaginary zeros always come in pairs, so make sure you fill that in right here. You can never have just one imaginary 0. Okay? Do you look, I can't remember if you do. Have you seen I before? Did you do it with quadratics maybe in math too? Like, have you seen that letter in math before? I'm seeing some of you nod yes. Does anybody remember what it means? It means the square root of -1. Because if you think about the square root of -1, square roots mean what number times itself equals that value, right? So like when we do the square root of 4, it's saying what number times itself equals 4. And that is 2, right? Square root of 4 equals 2, because 2 times 2 equals 4. Is there a number that you can multiply by itself that will give you -1? if I did 1 times 1, it would give me positive 1, right? If I did negative 1 times negative 1, what would I get? Still positive 1, right? There's no number that you can multiply by itself that'll give you negative 1. But sometimes in the process of solving equations, you end up with a negative underneath the square root. And when you get that negative underneath the square root, sometimes there is still there's an answer that you can get to. But you have to be able to deal with that negative under the square root to do that. So mathematicians decided that they were going to call the square root of negative 1 I, and then they can use that. It has different properties to be able to solve equations. We don't have to go into great detail with this here because we mostly need to know that they exist and not quite as much how to solve them. Unit 3, if you guys have friends that are in Honors Math 3 right now with Ms. Martin, Unit 3 is where we really start to branch off from the honors class because there are a lot of things that Ms. Martin makes them do with the eyes that she goes into more depth with. She also makes them do a lot more things by hand in this unit that I'm going to make you guys do by hand. This is one of the big sections where there's a pretty big difference between the honors and the regular here. So just know that this I right here, this imaginary value, is a way of dealing with a negative under the square root. Okay. Also, it's one of my favorite things to use for good math jokes. You can see my banner back there says square root of negative 1 heart math. So what does it mean? I love math. So square root of negative 1 can be replaced with I. There's also a good joke back there on my board that has jokes on it where it's got a little, I can't remember which one it is. Oh, it's the one right there in the middle where it says mathematical insults. And it's got this little boy over here that's calling the other one square root of negative 16. What's he calling him? Anybody know? I'll tell you, square root of negative 16 could be written this way. It could be square root of 16 times the square root of negative 1. What's square root of 16? What's square root of negative 1? It's imaginary. It's I. He's calling the other boy 4 eyes. He's got glasses on. So, it's a good joke. Y'all want to laugh, don't you? It's good. So, if you find good math jokes, send them to me and I'll print them out and put them on my board, if they're appropriate. James, oh gosh, what's James' last name? James sent me a few I couldn't put on the board last year. But if you find a good math joke, send it to me. They're my favorite jokes. So what the big thing we're going to be looking at today is we're going to be looking at knowing how many zeros we have and whether they're real or imaginary zeros. So real zeros are going to be visible on the graph, so you can see them. They're x-intercepts, but they can have different multiplicities, so they can count like more than once. So real zeros with an odd multiplicity will cross the x-axis. Real zeros with an even multiplicity will touch the x-axis but not cross it. Okay, so let's look at what we're supposed to do here for this problem. So at this point, we're not worried about imaginary zeros. We're only worried about real zeros. If you got AirPods in, Joey, please take that out. Heston, take yours out. Anybody else, please take those out. All right, so zeros are going to be x-intercepts, places where we cross the x-axis. So right here at -2, right here at 0, and right here at 1. So my zeros, my real zeros, are x equals -2, x equals 0, and x equals 1. So if I have odd multiplicity, that means that 0 only counts, it could count 1 time, it could count 3 times, it could count 5 times. Most of the time it's just 1. Then I'm going to cross the graph, cross the x-axis. So that would be right here. I cross the x-axis at 0. It would also be over here at 1. I cross the x-axis at 1. Both of these right here have odd multiplicity. They only count 1 time or 3 times or 5 times. But at -2, do I cross the x-axis? Do I go across it? No. I sort of bounce off of the x-axis, right? It goes down, it barely touches, and then it goes back up. That is what it looks like when you have even multiplicity, meaning that that 0 right there counts more than once. It has to count at least 2 times. So that is even multiplicity there. Okay? So look at the next one, find all of those zeros, and tell whether they have even or odd multiplicity. So you're looking for those x-intercepts, and you're going to tell, thank you, whether it's even or odd multiplicity. Okay, I am not talking about the number being odd. Is 0 odd? No. If the graph crosses the x-axis at that point, then it is odd multiplicity. If it bounces, if it just like touches and goes back up, then it's going to be even multiplicity. All right, so Samara, what did you get for the real zeros here? All right, 1, 3, -1, and 0. Okay, very good. All right, Samara, which ones of those have odd multiplicity? -1 and 0. Both of these are odd. And again, not because the number's odd, but because right here at -1 and at 0, your graph crosses the line. Sophia, at 1 and 3, do we have even or odd multiplicity? At 1 right here and at 3. Okay, even. Very good. And that is because we do not cross the x-axis there. We just bounce, right? Okay. Now, real zeros can be found from the graph. We can't tell anything much about the imaginary zeros from the graph. So, what you're going to see for a lot of these problems is they're going to give you information about the function along with a graph. Okay? So, the function to the left is a 5th degree polynomial. That's important. 5th degree polynomial. Determine the number of real and imaginary zeros for this function. Okay? So, in this case, if I have 5th degree polynomial, then I have to have 5 zeros. They do not have to be 5 distinct zeros, but I have to have 5 zeros. There are there's more than one answer to this problem, so there's a couple of different ways that you could answer this. Okay, so let's just talk about the real zeros first, because that's what we can see. Right here at 0, I definitely have a real 0 across the x-axis. What do I know, Richard, about that multiplicity? Is it going to be even or is it odd? If I cross the x-axis, it's odd. Okay? And so at 2, at x equals 2, there, Carson, is that going to be even or odd? That one's even. So there's a few different ways this could happen. Okay, there's more than one answer for this that could be correct. So I could have x equals 0 could be odd. What's the lowest odd number I could have for it? What's the lowest odd number? What's the lowest positive odd number? 1, right? So I could just have a multiplicity of 1 for that. And then I could have at x equals 2, I have even multiplicity there. So Jalissa, what's the lowest even multiplicity I could have? What's our lowest even number? Well, lowest, let's go lowest that is true. 0 is your like lowest even number. If I don't specifically say it's got to be positive. So if it has to be positive, 0 wouldn't count. What would your multiplicity be for that? It'd be 2, right? That's your lowest positive even number, right? Because you can't have if you have a multiplicity of 0, then it doesn't really count. So we can't have a multiplicity of 0. Multiplicities have to be positive numbers there. So I could have, right here, this would be considered 3 zeros. It is only 2 distinct zeros, like 2 different places where you cross the x-axis, but it's 3 zeros when it comes to the fundamental theorem of algebra, because that x equals 2 would count twice. So the most common answer for this is that you would have 3 real zeros. And if you have 3 real zeros, then I have to have, like I have 5th degree, I have to have 5 zeros. So if I've got 3 real zeros that I could see, how many imaginary zeros would I have to have? 2. Because this has to add up to 5. So this would be the most common answer that you would see. It's not the only thing that could happen, because I could have x equals 0 could have a multiplicity of 3, and x equals 2 could have a multiplicity of 2, and they could all be real zeros. So it could be 5 and 0. Or I could have 1 and 4, and they could all be real zeros. Something really important, a note you might want to make here. Imaginary zeros, we already said, always come in pairs. So this right here always has to be an even number. So imaginary zeros, you cannot have an odd number for that. So what a lot of people will do on this is they'll say there's 2 real zeros and there's 3 imaginary. And I would know automatically that has to be wrong, because you can't have 3 imaginary. Imaginaries have to come in pairs. And what they've done, if they say there's 2 real zeros, is they're not counting that one right there twice for that. All right, let's keep going, because I know this is kind of confusing at first, like what's going on here. All right, so the function to the left is a 6th degree polynomial function. Determine the number of real and imaginary zeros for this function. So if I look at this graph right here, let's just talk about those zeros. Right here at x equals 0, I have a 0 that bounces off of the graph. So that means it has to have even multiplicity. What's the very lowest multiplicity it could have being even? It'd be 2, right? Then I have x equals 1 right here. That could be a multiplicity of 1. I've got x equals 2. That could be a multiplicity of 1. I've got x equals 3. That's a multiplicity of 1. And I've got x equals 4. That's a multiplicity of 1. Now, in this particular case, there's only one answer you can give me because this is a 6th-degree polynomial. So how many zeros am I supposed to have? I'm supposed to have 6 zeros, right? The degree has to match the number of zeros every time. So this would have 6 real zeros, and if it already has 6 real, it can't have any imaginary for that. Now, when you look at them, it's only 5 distinct zeros, right? But why does this still count as 6? Because of that multiplicity of 2. So like x equals 0 counts twice for that. Okay, questions? Okay, let's look at something different here. The function f of x equals, it gives us the equation, has zeros at x equals 5 and x equals plus or minus 3i. Tell the number of real and imaginary zeros for f of x. Okay, so right here, they tell me for sure I've got a 0 at 5, and they tell me for sure I've got a 0 at x equals plus or minus 3i. Now, x equals 5, I can see that on the graph. Plus or minus 3i, am I going to be able to see that on the graph? Those are imaginary numbers. They don't show up on a graph. Okay? So, let's graph this on Desmos. So, pull up Desmos there. I want you to graph that for me. So, everybody's looking at it on their screen. And I'll graph it up here as well. Now, they did not give us all the information they could have given us in this problem. And these sometimes are pretty hard to see. Like if I zoom out, it just starts to look like a line. So you have to be careful with zooming out here. But what you really care about are those zeros, those places you cross the x-axis or touch the x-axis. I can see them good enough here. If I want a better picture, I could make my y-axis go down to like -50 or maybe even 100 or less. This one's just a hard one to get a good picture of, really. Let's just go with the home view right here. So they already told me I have a 0 at x equals 5. They told me I've got 2 imaginary zeros, right? Do I have any more zeros? Do I have any more zeros that I can see? What is a 0? What's a real 0? What's it look like on the graph? It crosses or just touches the x-axis, right? If we can't answer that question, and I realize some of you may just not want to like volunteer the information because you don't like to say things out loud in class, but if we can't answer that question, what's a real 0 look like on the graph, then we're going to do terrible, terrible. It's the main idea right here, right? So a real 0 is where we cross the x-axis. We got one at 5. They already told us about that one. We also have one over here at -1. Okay? And when I look at that one, does it cross the x-axis there? My graph does not cross the x-axis. So, Joey, if it doesn't cross the x-axis, what type of multiplicity do I have? What? Okay, so multiplicity is going to be even. So it's even when you don't cross the x-axis. That means it counts more than once, right? You know, if I asked all of you to, you know, give me your favorite, you know, number, I might have repetitive numbers, right? So like it would be more than once. It would count more than once. That's what's happening right here. That right there counts more than once. So when we answer this question right here, I have got at x equals 5, I know that's an odd multiplicity. At x equals -1, I know it's an even multiplicity. Also, I know I've got imaginaries for this because they told me I have imaginaries for this, right? And what does it mean when they put the plus or minus in front? It means it could be either one, right? It's really two answers. So both of these are imaginary. There's got to be at least two imaginary zeros. And then, Adela, how many zeros am I going to have all together for this? Fundamental theorem of algebra tells us our degree has to match our number of zeros. So if I look for the degree of this function, what is it? Okay, with how many, with what degree? 5. It's a polynomial with a degree of 5, right? So if my degree right here is 5, that's telling me I've got 5 zeros, right? And I already know I got 2 imaginary. And when I look at the graph, I can see that I've got x equals 5. It's going to have an odd multiplicity, so that's going to have to be a multiplicity of 1. And I got x equals -1, and that's got even multiplicity, so that's going to have to be a multiplicity of 2. So I got 3 real zeros. If you think about listing them out, I would list out x equals 5. I would list x equals -1 twice, and I'd have x equals 3i, and I would have x equals -3i. Those would have to be my 5 zeros here. Remember, again, that this has to always be even. Right there. Always has to be an even number. Okay. Our next one, type that one into Desmos for me. All right, so when I look at that graph there, Caden, how many real zeros do I have on that graph? I got 2, right? I've got one at -2 and I got one at 4. And both of those cross the x-axis, so do I have even or odd multiplicity for those? What? Not even. It's odd. Crossing is odd. Bouncing would be even, right? So probably those only count once. They could count 3 times, 5 times, 7 times, but not for this particular problem. So if I am looking at this, Jamaja, how many zeros am I supposed to have for this particular function? If I look at my original equation, I'm supposed to have 4. The highest degree right here is 4. That tells me I got 4 zeros total. Okay? And looking at that graph, I know I had x equals -2, and I had x equals +4, I think. Did I write that down right? Is that right? Okay? So I got those two. They're real zeros. I'm only supposed to have 4 zeros. The problem tells me I've got x equals 2 plus I. Okay? Both of these have to be odd, so they can't count twice. So, and what did we say about imaginary zeros? They always have to come in pairs. So they didn't give us both imaginary zeros here. But if I have one, I know I've got to have another one that goes with it. Right? In fact, it's going to be something called the conjugate pair. That's not terribly important. We just need to know that it exists. It means 2 minus I is also going to be a 0 there. So if 2 plus I is a 0, and 2 minus I is going to be a 0. If positive 3i is a 0, negative 3i is a 0. They gave us both of them here. So I'm going to have 2 imaginary zeros and 2 real zeros. And each one of those zeros only count one time. Okay, here. All right. Another thing that we have to talk about for these problems is end behavior. We did end behavior with log functions. It was not our strongest. But all you're really doing for end behavior is you're talking about what happens on the ends of the graph, right? Polynomials are a little bit easier than logs and exponentials because logs and exponentials, they could either go up to positive infinity, they could go down to negative infinity, or they could even out at a number. So there were more options for that, particularly exponentials that had horizontal asymptotes. Polynomials can only go up or down. So your answers for these should only be positive or negative infinity. You should not get a number for these, right? So, if we look at this graph right here, we learned whenever we were doing end behavior that as x approaches negative infinity tells us that we're looking at which side of the graph? Left. And as x approaches positive infinity tells us that we're looking at the right side of the graph. So on the left side here, Joey, if we look at this graph, on the left side, if I start in the middle and go towards the left, what does my graph do, Joey? Does it go to positive infinity or negative infinity? Okay. Can you say that again, please? Positive infinity. Very good. Okay? And then, Sophie, on the right side, if I trace my graph out on the right side, on the end, am I going to positive infinity or negative infinity? Also positive infinity. A lot of these you're going to have the graph for, so you should be able to just graph it and see. But there's this little chart over here that also can help you. If you have an even degree, then the ends have to go in the same direction. Okay? If you have a positive leading coefficient, meaning the number in front of your highest degree term is positive, they'll both go up. If you have a negative, they'll both go down. If it's odd, they'll go opposite directions. Okay? So, do end behavior on these next ones here. Carson, what'd you get? As x approaches negative infinity, y approaches positive infinity, because on that left side, you're going up. Okay? And on the right side, as x approaches positive infinity, y approaches negative infinity, because that side goes down. Okay? Hector, what about number 8? As x approaches negative infinity, y approaches negative infinity. If you graph it, you can see that left side is going to be going down. And Hector, as x approaches positive infinity, what do you get for your y? I don't think so. It should be positive infinity for that. So I have not graphed this, but I'm using the shortcut. I am seeing that I've got odd degree. And odd degree means that the sides will go the opposite direction. Okay? And then if you look at the number in front, this tells you what the right side will do. So if this is a positive 3, the right side will go to positive infinity. And since it's an odd degree, they got to go opposite direction, so it'll be negative infinity. So you can do it without graphing it, right? The number in front of your highest exponent will tell you what the right side does. And then even or odd will tell you whether they go same direction or opposite direction. But you definitely can graph that as well. That right side should be going up there. So if I'm using the shortcut on number 9, I'm going to look at the number in front of the highest degree term. So that's this negative 2 right here. It is negative. That tells me that the right side will go down, so it'll be negative infinity. Okay? Then I look at the degree, the highest degree, which is 4. It is even, which tells me they go the same direction, so I will also have negative infinity here. Is that what you guys saw on the graph also? So you don't have to use the shortcut. You can just graph these. Shortcut just makes you faster with that if you know that information. It's a great trick for, like ACT or something where time really matters, but in this class you'll have time to graph it if you need to. Okay? All right, we got one more slide that we're going to look at. Another question that you might be asked is just how many possible solutions or roots are there for each polynomial? So, in this case, they are giving you an equation, not a function, right? So, if we wanted to graph it, we would need to graph, like we'd need to move everything to one side. But, whenever this is the case, fundamental theorem of algebra can be applied to equations as well, okay? So, if I have an equation that has a highest exponent of 2, right? And the difference here is I've got, like, an equation is going to have an equal sign in it, right? A function is going to be like f of x equals some expression, right? It's not equal to a number. It's just an expression that you can graph. These are equations that could be solved where you get the answers where x equals 2 and x equals 7 or something like that. But the highest degree is also how many possible solutions do you have, right? So on number 10, the answer is 2. You could have 2 solutions. You will have 2 solutions. They could be imaginary. They might be repeated. So you could have like x equals 4 and x equals 4. Like it might be repeated, but there will be 2 of them. So if I look at 11, Nate, how many possible solutions do I have? I've got 5. It's your highest degree. You will have 5. Now, they might not all be real solutions. Some of them could be imaginary, but you will have 5. And they could be repeated. Let's see. Heston, what about number 12? How many solutions am I going to have to that? Just 1. Because that x right there has an exponent of 1 with it, right? And we could solve that one pretty easily. Add 3. Right now, we know how to do that one. Zoe, what about number 13? How many solutions could I have to that one? Yes, I almost missed the 8 and was going to say 6. But the 8 right there is your highest exponent, so you're going to have 8 solutions to that. So, throughout the unit, we're going to learn how to find some of those solutions. We're going to do a lot of different stuff with this. But the main idea is that the degree matches the number of the roots or solutions for this. So,